How do you do? The topic of the fourth lecture is electric energy of a capacitor and the direct current. At the end of this lecture, you will learn energy and energy density of an electrostatic field, movement of charges in the electric field, electric current and the current density, Ohm's law, work and power of a direct current, Joule-Lenz law, and its differential form. To understand this lecture, you will need to know the following vocabulary: power, мощность, watt, capacitor, конденсатор, parallel plate capacitor, плоский конденсатор, жазық конденсатор, drift velocity, скорость дрейфа, resistivity, удельное сопротивление, меньшікті кедергі, electromotive force, электродвижущая сила, электрқозғауыш күш. So just now we will consider the energy of a charged capacitor. So the electric potential energy of a capacitor is just equal to the amount of work required to charge it. That is, to separate opposite charges and place them on different conductors. When the capacitor is discharged, the stored energy is recovered as work done by electric forces. So let us obtain the expression for energy of a charged capacitor. So let Q and U be the charge and potential difference respectively at an intermediate stage during a charging process. Then the voltage will be equal to the ratio of the charge to the capacitance of the capacitor. So the work needed to transfer additional element of charge, the Q, will be equal to the product of the voltage and this element of charge being transferred. So substitution of the voltage via charge and capacitance will give us the expression for the work required to transfer an element of charge, the Q. EDS, this work is equal to the ratio of the product of the charge Q and the Q to the capacitance of the capacitor. The total work needed to increase the capacitor charge from 0 to a final value Q, so will be obtained via integral of a small amount of works needed to transfer element of charges, and then we get the total work is equal to the ratio of the charge squared to the twice of the capacitance. If we define the potential energy of an uncharged capacitor to be 0, then W in equation 2 is equal to the potential energy of the charged capacitor. So EDS, we can say that this expression is the energy of a charged capacitor. So the final stored charge Q is equal to the product of the capacitance and voltage. So the potential energy stored in a capacitor is can be defined by one of these three expressions. So Q squared over twice of the capacitance, or the half of the product of the capacitance and the squared voltage, or the half of the product of the charge and voltage. So we can say that capacitor stores both energy and charge. So just now we will consider electric current. What is electric current? Electric current is a flow of charges through a conductor in a specified direction. Electric field produced under two conditions, that is, existence of the charged particles and the existence of an electric field. Under the electric field, the electrons moved opposite to the field, and the net flow opposite to the field makes the electric current through the conductor. The electrons suffer collisions with atoms of the conductor. Therefore, their motion is not accelerated, but they drift opposite to the field. Their average drift velocity is very low, of the order 10 to minus third power meter per second in a typical case. However, the exchange of drift among the electrons are at the rate of speed of light. Therefore, current flows with the speed of light under the effect of an electric field. So that is, here we have the figure which explain the current in the complete circuit. So that is a scheme of a complete circuit. That is the real complete circuit. Very simple. So we have the source of electromotive force and the resistor or lamp through which the current flows. And inside this source of energy, or inside the battery, the charges move from negative charge to the from negative terminal to the positive terminal under the action of non-electrostatic forces. But in the external, along the external circuit, the charges move under the action of the electric field. The action of the electric field. So here, between the terminals of the battery, the voltage is equal U, and it is equal to the difference between the electromotive force and minus the potential drop inside this battery. So because the battery has its own internal resistance, that is why here we have a potential drop inside the battery. And that is why the potential difference in the external circuit between the terminals of the battery is equal to this difference. Potential difference, called the terminal voltage, is less than the electromotive force because of the term I small r, the potential drop across the internal resistance. So that is the potential drop inside the battery due to the resistance, internal resistance R. And the current in the external circuit connected to the source terminals, negative and positive, is determined by this expression. It is determined by the external resistance. So combining these two expressions for the potential drop or the voltage across the terminals of the battery, we get the expression for the Ohm's law for a complete circuit. It states that the current through the complete circuit is directly proportional to the electromotive force and inversely proportional to the sum of the external and the internal resistances. The moving charges collide with atoms in the resistor and transfer some of their energy to these atoms. The internal energy of the resistor increases. It is heated due to its temperature increase. It is said that the potential energy of an electric current is converted into the heat energy dissipated in the resistor. This energy is determined by Joule-Lenz law, which states the energy dissipated in the resistor is equal to the product of the squared current, voltage, and time. It is determined by this expression. That is the heat dissipated in the resistor. So let us make the summary of our lecture. The electric potential energy stored in a charge capacitor is defined by this expression, by one of these expressions. The energy density of an electrostatic field is directly proportional to the square of the electric field. And the energy density of an electrostatic field does not depend upon the configuration of the electric field. It depends only upon the magnitude of the electric field. The greater is the electric field, the greater will be the energy density. Electric current and current densities are defined by these expressions. So the current is the amount of charges that flow through the cross-sectional area of a conductor per unit time. And the current density is the amount of charges that flow through the unit cross-sectional area per unit time. So the current is a scalar quantity, and current density is a vector quantity. Ohm's law for a circuit element is defined as current equal to the ratio of the voltage to the resistance of the resistor. Ohm's law for a closed circuit is defined as current is equal to the ratio of the electromotive force to the sum of the external and the internal resistances. Heat energy and power taken out or in the electric circuit defined by these expressions. That is, these are expressions for the heat energy taken out in the electric circuit, and that is the expression for the power taken out in the electric field. And the power does not depend upon the time. That is the end of our lecture. Thank you for your attention.